So this is a lab pertaining to the chemical bonding chapter that we did earlier. These two round thingies over here are basically atoms, okay, and this graph shows you the plot of energy, potential energy specifically, versus the distance between atoms. So you can see that if I move this atom to the left and to the right, this blue guy also moves. Yeah, so it seems like that's what it is. It's the distance from this point, this fixed pinned atom, and this. Do you follow that? Easy enough, right? Okay, and then you see that there are some atoms listed on top. Yeah, that's just the control of atoms. There are different atoms listed over here. I'll change it as and when necessary. I will click all these things. Yeah, I will click on this component forces. You'll see what that is in a short time. Okay. Okay, let's get started. And yeah, as usual in all the simulation, there's a pause and a play button. As of now, this simulation is paused. So I will select the atoms to be oxygen. Okay, the pinned atom and the moving atom to be oxygen. Now that I've done that, I want to move it away at this point. Yeah, and I have checked this component forces box. So note that the potential energy should be 0, which is cool. Yeah, this red line is in line with the 0, that small thin line. So you agree with that? Its potential energy is 0 at a distance far away from the pinned atom. Make sense? Yeah, it makes sense. So if there's nothing close to this atom, then it would have no effect on it. As I go closer though, the effect of the other atom would be felt. So let's see. I have shown the component forces, and it seems like the yellow arrow would show attractive forces and the purple arrow or the pink arrow would show repulsion. So as I move it closer, after a certain point, I have overlapped it quite a bit, you see. After a large overlap, these yellow forces start showing up. That means that if I move these atoms closer and closer, this is nothing but the attraction between the electrons of one atom and the nucleus of the other. Do you agree with that? This is something we've done in class already, yeah? Nothing very complicated. But this is just a very cool simulation to show you the same thing. So the potential energy now is falling. That makes sense as well, because the criteria for bond formation or for any of that is basically the fact that the total energy should be minimized, and that seems to be happening when I have 0 potential energy here. As soon as I bring it closer, the energy starts to fall. It's going down this red curve. Yes? Do you agree with that? That potential energy seems to be reducing just by looking at the curve. Exactly, negative potential energy. Negative potential energy. So potential energy, remember, is just the energy in relation to another particle due to its position. A simple example is gravitational potential energy. Now, that's the easiest one to explain. But with respect to bonds, remember I told you that they try and attain a configuration that has the lowest energy. What energy are we talking about? We're talking about the potential energy. Why? Because they are two atoms and their effects will be felt on each other. Hence, the lowest possible energy, which would be in this graph, it would be at this point. You have said something very interesting, which is why I'm skipping a little bit ahead. You'll see that very soon. Yes? So it is possible to have positive or negative value. That really doesn't matter. That depends on the reference point. Our reference point was that far away it's 0. Alright? And as the atoms come closer, the yellow lines become bigger, which means that force of attraction is more, which means the energy should lower itself. Cool? Does that make sense? Excellent. So now most of the atom is empty space. Yeah, so that's why so much of overlapping is actually possible. So, and remember that this pink thing is there. A very, very small pink thing is there. I don't think you can hardly see it. If you know it's there, only then can you look for it. But as soon as I move this closer, the pink arrow starts to become slightly bigger. Now you can maybe see it, yeah, a little bit. The pink arrow is existent now. It's possible to view it. Really tiny pink arrow, yeah. What is that? That is basically repulsion between the two nuclei of these atoms, because nuclei are positively charged, and as you bring the atoms closer together, they would tend to repel. So there are two forces acting, and depending on which force is larger, this energy would either fall or rise. At this point it's still falling pretty steeply, correct? So what do you think is going to happen if I keep moving this closer and closer? Any ideas? Alright, don't worry about it. Let's see. As soon as I keep moving it closer and closer, you can see that the pink arrow keeps becoming bigger. Right? So maybe at some point, basically when I say the pink arrow is increasing, that means the net force is reducing. Yeah, this seems to be balancing each other. Not balancing right now, but almost. Yeah. Earlier the pink force was negligible. Now the pink force is pretty big compared to this yellow force. Just look at one pair of forces. Yeah, this pink force and this yellow force. The one behind refers to the other atom. Okay. Does that make sense? Okay, excellent. So the attractive forces, the net force is still attractive, but the repulsive forces seem to be increasing really quickly, and that makes sense. If remember, the electrons are scattered all over the place. The nucleus has a very strong positive charge. So if I bring it closer to each, if I bring the atoms closer, then the nuclear repulsion will be much larger than the attraction. Initially, sure, the attraction was large, but as you go closer and closer, the repulsion is very large. Let's test this theory. At some point, look at now, notice this blue dot that is moving down this slope, right? At some point, you keep increasing it. At this point specifically, both of them are equal, and well, it's out of the screen, I understand that, but that's how strong the forces are. That's how strong both the attractive and repulsive forces are. They're really strong, but they cancel each other out. Do you see that right now? That they cancel each other out? From this diagram, I understand that you obviously cannot tell from this thing because out of the screen. But if it is at a lowest potential energy configuration, then hey, that means that no, the nuclei are not touching. If the nuclei would touch, see, if the nuclei would touch, then the distance between them would be 0. It's just a place at which, but that's not possible, as you can see. A nuclei will never touch because you can see that the energy goes really high up. This red line basically is trying to tell you the total potential energy. Yellow line over here is the attractive potential energy, the attractive force, and the pink line is the repulsive force. Now at some point they become equal. That makes sense, right? See, if initially there was a lot of attractive force and then the repulsive force started off, but now the repulsive force is really large. So if I keep bringing it closer, at some random point they would be equal. Does that make sense theoretically at least? Okay. Now, at the point that these forces are equal, potential energy reaches its lowest point. Do you agree with that? Because after this point, where they're equal, the attractive force will be, the repulsive force will be greater than the attractive force, which would increase the increase the total potential energy as well. So only at the point where the attractive and the repulsive forces are equal would the energy, potential and the total potential energy be the least. Pretty cool, right? That makes sense? Excellent. What does that mean? Lowest possible energy means bond formation. Do you agree with that? Okay, very nice. So basically the important thing to take away from here is that two forces, or well, many other forces, in a simplified diagram, there are just two forces, attractive and repulsive forces, and they are in balance, and this is the nearest that they can approach the atoms. If the atoms come any closer, then the potential energy becomes so high. You see that? I just moved it a little bit and it goes straight up. Yeah? And it's gone out of this. So it's so high that they would just bounce back. Yeah, it's like I don't know what sort of example to give you to like magnets. Think of two magnets. Yeah, not the best example, but if I have both the north poles together and I bring it really close, they repel, right? This is not the best example, but I'm just trying to tell you the repulsive force, the effect of the repulsive force. Clearly here there are two forces that are at play, but you can understand what happens here is if I bring it too close, potential is really high, which means it would go wham, it would go right out. Yeah, it would just shoot out. Does that make sense? Okay, so the lowest possible energy would be at this point where the forces are equal, and that basically the distance between these two, this sigma that you see here, right? This sigma, you see sigma and epsilon, they're basically just Greek letters. You see that, right? Sigma over here and epsilon is written over here. So sigma, the length sigma, is nothing but the bond length. Yeah, the shortest possible bond length. So theoretically, two oxygen atoms would have this separation between them. So we make this theory up, and you have a lot of math, and then we test it with actual instruments, and if that works, then yeah, this theory works. So this is what was done. This is the experiment that was done to figure it out. Now, oxygen-oxygen bond is a pretty strong bond. Yeah, you can see the extent of overlap is really high. It's almost like half in, right? So the reduction in potential energy is also very significant. Yeah, a large distance you can see here. It's a sharp curve and it's a large dip as well, right? So basically, if the reduction in potential energy is very large, then the bond is really strong. Okay, so two things give you the strength of the bond. One would be the distance between the bonds, yeah, between the two atoms. That if it's a short distance, then it's a strong bond. Second thing would be the depth of this potential energy gap, or this basically, yeah, this distance, epsilon. So if both of these low sigma, high epsilon would mean a very, very strong bond. Nothing, you don't have to remember all this. Just looking at the graph, yeah, epsilon and sigma are just alphabets. You can figure it out from the graph, right? Alright, let's see what happens if we change the atoms. Yeah, let's reset this and let's take something like neon. Yeah, it's already, the preset is already set to neon. Now straight away you know that this bond is going to be really, really weak. Large sigma, very low epsilon. Yes? Do you agree with me? Let me pause this simulation before we go ahead. Okay, excellent. Now let's see if our theory works. Now we do the same thing. We take these atoms closer slowly. I'm moving this towards the pinned atom, and hey, the yellow force is there, but the pink force starts right away. Yeah, the repulsion also is really strong. You see that? At this point, only at this point is the yellow force greater than the pink force. Very, very small. Can you see this? As soon as I go a little bit closer, yeah, they are equal. So the extent of overlapping is a lot less than that of oxygen, right? So this means that the negatively charged electrons of each atom are being attracted by the positively charged nucleus of the other atom, and that's the attractive force. And basically, now the degree of overlap is really, really small, and the repulsive forces are shown by the pink arrows. Now these arise because the repulsion between the negatively charged electrons of the two atoms and the repulsion between the nuclei of the two atoms, both of them. Remember that neon has a fully filled electrons, and a lot of electrons repelling each other, and the nuclei also repelling each other. Does that make sense? That's why the repulsive force is so high already. Okay, excellent. So now potential energy has reached its lowest point. This would be the bond length. That's why it's so large. The distance between nuclei, it's much larger. And this is a weak bond because, well, the overlap is very low. Yeah, the energy, the epsilon also is really low. So clearly what we have seen is that when we compare this to the oxygen bond, we can conclude that the extent of overlap is greater for strong bonds. That's the first point that I wanted to take away from this. The second point would be the potential energy lowering is much more for strong bonds. The third point would be the bond length is much smaller for strong bonds. And lastly, the magnitudes of attractive and repulsive forces are much greater for strong bonds. Remember, magnitudes of both, not just attractive, but attractive and repulsive forces are much greater for strong bonds. Do you agree with all of these points? Any confusion? Do you have any questions so far? That was it about this particular part of the simulation. Any questions so far? Ashna, are you there? You have a question. Exactly. That's what, see, remember, your question is, do the bonds form only at the point where attractive and repulsive forces are equal? Remember, the definition of bond formation is attaining the lowest energy state. Now, for it to attain the lowest energy state, if there was no repulsive force, then you could keep bringing them closer and closer together, and the potential energy would keep going lower and lower and lower, which means the bond would be stronger and stronger. But because of the repulsive force, there is a dip and then a sudden rise, right? So you want to reach a point at which they are both equal, which would be given at the bottom of the well. Yeah, this potential energy well, this is a potential energy well, so to speak, and the bottom of the well, this point would give you the lowest energy state, right? And the lowest energy state happens to be at the point where the attractive and the repulsive forces are equal. So the strongest bond would form when this happens. Sure, it could be a little off and a little closer. You can do a lot of things. There are many other factors at play, but theoretically at this point, this is the best explanation. Okay? Clear? The other way around. It's much easier to form an oxygen bond because it releases a lot more energy. Remember, when bonds form, energy is released. When bonds are broken, so it's much easier to break the neon bond because the energy input is really low. So you have to keep both those things in mind. The first point obviously is that energy is released when bonds are formed. You need energy to break bonds. So, do you understand that? Much harder to break the bond, break the oxygen bond, much easier to form the bond as well. Cool? And the opposite in this case, yeah? Very hard to form this bond because, well, very low energy release, and very easy to break it, this neon bond. Okay, excellent. Any other questions? Okay, hold on. I'm just going to pause this recording and we'll get started in just a couple of seconds. This on the left hand side is, well, a gun. It's an alpha particle gun. Okay, alpha particle, remember, are just simply doubly charged helium atoms. Let's look at that. We'll look at that in some time. What is a doubly charged helium atom and all that. Although you guys already know this. Okay, let's. There are a few settings on the right hand side. You can see that the small thing that is rotating on the side. Yeah, you see it once in a while. Just look at this top right, top left. Okay, yeah, there it went. That's basically the electronic orbit. Yeah, the closest electron. You see that? The small electron just roaming about towards the edge of the screen. Yes? There it goes, there at the bottom, and here it's going to come here in some time now. Wait for it. There you go. Okay, that's the electron. So that means that that's the minimum distance from the nucleus. Yeah, and the center guy is the nucleus. Red guys are the protons, the grey ones are the neutrons. Alpha particles, well, clearly would have 2 neutrons and 2 protons. I'm going to set the energy of these particles to the maximum limit. I'll also click on the short traces thing. You'll know what this is in some time. And atomic properties are this. This is gold. Yeah, gold has 79 protons and 180 neutrons. So, and this distance that you see is 150 Fermi, femtometers. Yeah, femtometer. And that's basically 10 power minus 15 meters. That's how small that is. So this part is a highly magnified thing. The gun is striking this target. Yeah, you see this gun and there's a small target right next to it. This is a highly magnified section of the same thing. Okay? Do you follow this whole setup? Do you understand it clearly? Okay, excellent. So let's get started. Here I'm just going to start the gun. Yeah, there's a small circle symbol there. So as soon as I start, you see that there are a lot of alpha particles, and you see that some of them are deflecting away and some weird stuff is happening. Okay, now I'm going to pause this. Now this short traces business was basically, it helps us to see where these electrons went. Yeah, their path basically. So you can see that most of these guys seem to pass away unhampered. Why do I say that? Remember, these are the alpha particles very, 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 very close to the nucleus. The normal size of an entire atom is much, much larger than just the nucleus. And remember, this is only the first electron orbit. So even in this, there are some that are not being really reflected. Yeah, obviously there's one guy, or that is being reflected at an angle almost at 180 degrees, or say 120 130 degrees. This guy is being deflected at a very large angle. Yeah, do you agree with all of this, everything I've said so far? So basically, as the trace comes closer to nucleus, the deflection starts to increase. Why do you think this is? Why does that happen? Why is it that these guys are being deflected very at a large angle compared to the ones that are further away? What do you think the reason is? Any ideas? Excellent, excellent. Because the alpha particle is completely positively charged, and well, it gets repelled by the nucleus, which is also completely positively charged. So and yeah, the repulsive force is really, really large, because the nucleus, as you can see, has 79 protons, so it has a plus 79 charge. So these guys, even halfway between, halfway between this, the nucleus and the electron orbit, like somewhere over here, these guys also getting deflected quite a bit. You can see that they are turning quite a lot. Now what do you think is going to happen if I use a lighter atom instead of this gold atom? If I use, say, calcium, what do you think is going to happen? How is it going to change? Let me just make the changes over here. What do you think is going to happen? Type away while I make the changes. Okay, so I've changed the central atom. I'm going to hit the gun again. Yeah, excellent. Exactly, that's what's going to happen. Let's see. Yeah, you were absolutely correct. The alpha particles still repel, but not as drastically. Only the ones really, really close to the nucleus get deflected. Rest of these guys are happy, and they go straight through. So we have reduced the number of protons, and that results in a lower repulsive force. Now the distance from edge to edge, remember, is 150 femtometers. Remember, if you put this into perspective, the angle that we are calling 90 degrees is not really 90 degrees. It's a very, very, very small angle. Yeah, we've zoomed, as you can see, 10 to the power 14 or 10 to the power 13 times. That's our zoom. So in actuality, most alpha particles pass through almost straight, but you do have there still are deflections, and that is what led to the discovery of the fact that, hey, the plum pudding model failed. Remember that? Remember the plum pudding model? Okay, let's look at the plum pudding model. We also have that here. So if it were to look like this, if the nucleus were to, the whole atom were to look like this, let's do the same thing. Yeah, we'll set the energy to maximum. We'll also click on show traces, and we're just going to pause the simulation before we do anything. So everything is set, and you can see that the plum pudding model is that, hey, the whole thing is our positive charges, and in the middle the electrons that are embedded. Right? That's a plum pudding model. Cool? Okay. So let me hit the gun and resume. Now what's happening? There are no deflections whatsoever. Why? Because the positive charge is spread throughout the atom, and it's not concentrated enough to deflect the incoming alpha particles. Sure, there is a positive charge, but it's not concentrated enough. And the attractive forces between the electron plums and the alpha particles cancel out most of the deflection. So there are two forces that are acting. Yeah? Do you agree? If the model were to be like this. Okay? Yeah, and according to this, there should be no deflection. As we saw earlier, that massive zoom. So by the way, that zoom that I showed you, this 150 femtometer, it's not a theoretical zoom. There are some very, very fancy instruments that actually reach those very close to those magnifications. Yeah.
need not be visual magnification. When you talk about magnification, we only assume that hey, you should be able to see it physically. What electron microscopes do is that they measure the change in magnetic field and the change in electric field and some very, very cool techniques to image an object. Okay, so it's not always just visual magnification, which is why it's possible to have such a large magnification. Does that make sense? So a pretty interesting idea. If you want, you could read up on this. There's the lenses that I use are electromagnetic lenses. Obviously, you don't use a concave or a convex lens. You use electromagnetic lenses that have a similar effect on electrons, and electrons focus on your target, and you get very cool pictures. Okay. Anyway, so it is possible to see those occasional differences, those occasional very, very large reflections. You know, the 180-degree thingies. So that is what led Rutherford to figure out that hey, there must be a large nucleus in the middle where all the protons are concentrated, which is why the whole thing was a really path-breaking discovery in modern science. Okay, this led to a lot of other very cool discoveries. So that was it about this Rutherford scattering bit. We have another simulation for you guys. Okay, I'm just going to pause this. Okay, cool. So this entire thing is a very cool simulation to play with. You can build your own atoms. This X marks the spot. This refers to all the nucleus. This central X is the nucleus. This first dotted line is the first orbit. The second dotted line, the second orbit circle is the second orbit. Okay. So what I can do is I have this whole set of protons, neutrons, and electrons that I can dump into this. I can make different atoms. I'm going to open all these these symbol readers out. The symbol reader, mass number reader, and charge readers out. Yeah, that's it. And these are the different particles. Let's get started. Okay. So yeah, you just need to make sure that they're all open, that all the plus signs are marked. Okay, just to be sure. Now let's drag one proton and dump it on the X. I'm also going to drag an electron, and notice that wherever I leave it, okay, I must leave it in the inner electron. If I go to the outer thing, it does not get accepted. So I must take it to the inner. Oh, sorry, that was not an electron. I'm so sorry. That was a neutron. Yeah, that's what it does. It goes, whatever I do. This is very interesting, by the way. Irrespective of, if I bring it close enough, it is automatically going to go to the innermost orbital. Does that make sense? Because that's the stable configuration of hydrogen. Why is that the stable configuration? Because hey, there's a nucleus in the middle and it attracts the electron close to itself. Okay, so remember that the first or the innermost orbital can hold only 2 electrons. Do you agree with that? The K shell, formally speaking. And the next innermost orbital or the second orbital can hold up to 8 electrons. This would be the L shell, L orbital. Now just take a look at the element display. It says that we have just created hydrogen. Now take a look at these 3 readers. The atomic number is clearly 1, which means the species has 1 proton, which makes sense. I just put in 1 proton. This also means that the neutral atom would contain 1 electron to neutralize the positive charge, which also is the case. The charge is 0 since I've added 1 electron. The mass number on the top left, yeah, this corner over here, shows a value of 1, which is simply the sum of nucleons, protons plus neutrons. So far so good? Okay. And the number of neutrons clearly would be the mass number minus the atomic number, which happens to be 0. With the mass number 0, atomic number 0. So visually we can see that there are no neutrons added. So hey, everything we've discussed so far makes sense. Charge is 0, which means the species is neutral. And take a look at the orbits. It seems like there are some partially empty orbitals. Yeah, because the K orbit can actually hold 2 electrons. So this is the reason why hydrogen on its own does not exist, because it is unstable. It has an extra empty space. Yeah, it has to bond with some other species to form stable species. This is why you get H2 always. The H bonds with itself and forms H2, the H2 molecule. Okay. Remember that I said it's unstable. This word over here says stable. This is not talking about chemical stability. This is talking about the stability of the nucleus, which we have not discussed so far in our classes. You will learn about the stability of the nucleus in higher classes. Okay, at this point we're talking about stability, chemical stability, whether it's reactive or non-reactive chemically. That's all we're talking about. Okay. So now if I remove this electron, what's going to happen? Remember, it has a now it's showing a plus ion over here. The symbol has changed over here from 0 to +1, and the net charge also has turned to +1. Okay. This is a single positively charged hydrogen cation. It has no partially incomplete shell of electrons. Hence, it is stable. Do you agree? This species is found in really strong acids, H2SO4, HCl. They form these H+ ions. It's a different thing altogether that H+ is a really tiny ion, and hence it decides to get surrounded by water molecules and forms larger ions. But in theory, it does exist as the H+ ion, although for a short time. Now, I'm just going to go ahead and add the electron that was already there, and I'm going to add an extra electron. Why? Because hey, I just told you that it is possible to have a stable atom, chemically if I have a fully filled orbital, and that's basically the negative ion, the hydrogen negative ion. Remember that now the charge become -1, mass number still is the same. So now, where do you see this? Yeah, the k orbital is completely full, L orbital is completely empty. So it seems like theoretically this could exist. This species is found as a metal hydride. Basically, it reacts with a more positive element and it forms a compound, and that compound is called a hydride. And usually, only metals are more positive than hydrogen. Some metals, not all metals by the way, are more electropositive than hydrogen. By more positive, more negative, I'm just talking about the reactivity series. Yeah, which again you guys have already studied. Remember? Okay, excellent. So let's that was a basic introduction to this build an atom thing. Let's just reset everything. Let me build another atom. After clicking all these things, I'm going to dump in 2 neutrons. I'm going to also dump in 2 protons, and what else do I have to do? Nothing. Let's just keep it. Okay, no. Let's first add electrons as well, so that we have a neutral atom. Okay, this is a neutral helium atom. Remember, the mass number is equal to sum of protons plus neutrons. I have added 2 neutrons and 2 protons, and hey, the mass number is 4. Okay, so that seems to be correct. Our theory seems to be correct. And also, the atomic number is equal to simply the number of protons, which is this number in red, which is 2. Since the number of electrons are equal to the number of protons, the net charge is 0. Okay. Also, there are no partially incomplete orbits. The k orbital is completely full. The L orbital is completely empty. So this is a stable compound. Do you agree? Chemically stable. Now, because it's completely full of electrons, the k shell, these atoms are chemically unreactive, and that's the theory behind it. So that's why helium is a noble gas. Does that make sense? Excellent. Now, if I remove 1 electron from this, I've got a positive ion. This is a singly charged helium cation, but the k orbital is partially incomplete. So this is not very stable. Yeah, so that's why you don't usually get H+. Whereas if I remove the second electron as well, here I have a helium +2 ion. Okay, and this is quite stable. Does that make sense? No partially filled electron, no partially filled orbitals. This is basically the alpha particles from the Rutherford experiment. Okay, alpha particle is the same as a doubly charged helium cation. We'll also discuss this in class, and this is how it's made. You strip off helium of its electrons. Alright? Okay, Let's build another atom now. Reset this. Let's build a lithium atom. Lithium atom that has a mass of say 6. Lithium seems to be the third element over here, so I'm going to first add proton, neutron, proton, neutron, proton, and neutron. Okay, so that is a lithium 6 atom, but it has a lot of charges, so I'm going to make it a neutral atom first. This is a neutral atom, neutral lithium atom. Now let me remove this electron. It doesn't fit. It's extra. It's making the whole thing really large and fat. So once I remove this, I have a positive ion. This is a really stable positive ion. Yeah, lithium plus. This a form of this is used in your cell phone battery, lithium ion batteries. This reacts with a couple of other compounds and it gives you really good batteries. High capacity, they call it. High capacity meaning really small size and a lot of charge. You will learn about charge and other things in the next year in physics. Okay. So since there is one excess proton compared to the number of electrons, clearly the charge is positive 1. And there are no partially empty orbitals. So this is a stable system. Do you agree with me? Okay. So lithium is pretty happy to lose that 1 electron and get into this stable state. Let's create another lithium atom. Instead of this whole thing, I'm going to go back and make it a neutral atom. Only thing extra I do is I added another neutron. So now number of protons is the same, number of electrons is the same. Just the number of neutrons that changes. So which one of the properties would change now? Would the atomic number change? Would the mass number change? Would the charge change? What do you think is going to change? Atomic mass. Excellent. That's what is shown over here. Masses become 7. Mass numbers become 7. So we have created another type of lithium called lithium 7. Remember I said lithium 6. I was referring to the mass of the lithium atom. Its chemical properties are very close to that of lithium 6. Its physical properties are different. These compounds that have the same atomic number and the same number of electrons as well, but different number of neutrons, are called isotopes since they have different masses. Okay? Yeah, excellent. Yeah, we've already discussed this in the later classes. So it's great and it's easy to understand. Now remember that since they have the same number of electrons and the configuration is the same, both isotopes will have similar chemical properties. They will both simply try to lose that extra electron and become a stable lithium positive ion. Alright? Make sense? Okay. Now let's create an oxygen atom. Oxygen would have 8 neutrons and 8 protons. Remember the atomic mass of oxygen was 16. So I'm just doing that. I keep dropping this guy. Hold on. Let me open up the. So remember, as I keep adding the protons, the mass number keeps, the atomic number keeps changing, which makes sense, yeah? That's what decides atomic number, the number of protons. Okay, here we go. Now I have a positive ion. Let me balance that out. Let me dump in 8 electrons as well. Okay, here we go. We are good. Now we have a neutral oxygen atom. Alright? Notice that it has an unfilled L orbital. Why do I say not unfilled, a partially filled L orbital? Do you agree with me when I say that? Yeah, because well, it's supposed to, it can hold 8, but it's only holding 6 electrons, which means that it has a dearth of 2 electrons. This is the reason why oxygen is in itself is an unstable atom. It is found in nature either as an oxygen molecule in which two atoms are combined, or with other elements with which it forms two bonds. So what choices does oxygen have? It can either gain 2 electrons or lose 6 electrons. Now it prefers to gain 2 electrons because that is easier to do. Easier, by easier I mean the energetics are lower. Does that make sense? So this causes oxygen to gain electrons and become a doubly charged anion. And these 2 electrons, let's do that. Let's add these 2 electrons and see what happens. I add this 1 electron, I add the second electron, and hey, I have a stable, nice ion, symmetric, and it has a charge of -2, mass number is the same, everything else is the same. This is nothing but the oxide anion that is really famed. Yeah, O2 minus. Cool? Okay, that was it for today's lab. Just going to stop the recording now.